Okay, so what we've been doing so far, what we did in the last lecture was we started the shock tube, right, and what we have to do now is to study the expansion fan, which is traveling to the left of the diaphragm. Once you break the diaphragm, there is an expansion fan which travels to the left of the shock tube, and that is something we're going to study now. Okay. Now, before we come to that, what we will try to understand is the very basic question as to how do these disturbances travel, and what do I mean by that, right? In the sense that, for example, the reason I am talking and you are able to hear, being at a certain distance from me, is to also say that I am creating a disturbance, right, in the surrounding around me, and that disturbance is traveling from here to where you are sitting, right. So, to give you very small examples, for example, on a pond, for example, the still water, and you throw a pebble, right, you see all these ripples being created, right. So, although you throw the stone only at a particular point, right, someone who is standing slightly away from that point is still able to see some changes in around him, right. So, therefore, this disturbance travels. So, what I am trying to say here is that the disturbance actually travels. Now, in our objective here, in doing these topics, in doing the shock tube, for example, is that we break the diaphragm, right, we break the diaphragm. Once you break the diaphragm, the effect of that, right, is felt along the shock tube. It is not just confined to the place where we break the diaphragm. So, that is why we kind of need to know how this disturbance, right, which is a normal shock to the right hand side and an expansion fan to the left of it, are traveling. How are they traveling, and how are we going to mathematically represent them? So, that is something that we will do today. So, what we will start out doing is try to look at the best way we can look at how waves travel. Okay. What do I mean by wave, right? So, you can, like I gave the example that say we have a still pond, right, and then you throw a pebble, then you see ripples. So, you can think of this sort of this sheet of paper, right. You can think of this sheet of paper, say, as the still water in the pond, right. You can think of this as that, and then when you say throw the pebble or the stone there, right, then what happens is that there is a disturbance created, and how is that created? So, then you see this. Okay. So, that you have still water like that, and then you see a ripple being created. Okay. Then a disturbance is created. Now, what is this disturbance, right? This disturbance could be in velocity, it could be in density, in pressure, temperature, etc., right, depending on what kind of flow you are looking at, right. So, in the same manner, you could also have that there is a flow which is moving, right, there is a flow which is moving like this. So, I can just think of that it is moving uniformly along moving like that, then suddenly, so as it is moving like this, I give it an impulse, and then that goes, impulse, and that goes. Now, the question is what happens to this disturbance, right, what happens to this disturbance over time and also in space. Okay. So, let us go ahead and try to look at this mathematically and see what we can gather, okay, what we can understand from there. So, we will write out equations and see if we can study the movement of waves, okay, or say basically the propagation of disturbances in the form of waves. Okay. So, let us go and do that. Okay. Now, like I said, when I say a disturbance, the disturbance could be a change in various properties, density, temperature, pressure, velocity, etc. So, let us just take for example, density, right. Now, let us say like so let us say this is the x direction, right, and say this is a density. Okay. This is a density, and so at some point, basically at some, say this is at say at some time we have right. Now, let us just say that this is the ambient density or the free stream density. Okay. This is undisturbed. So, we have a certain density which is this. Okay. And now, what I do is suddenly at say some instant of time, some x, so say at this point say x, right. So, at this point x I give this ambient, there is a certain disturbance. Okay. What is that? So, that is like a small disturbance. So, if I do that, so let us say it is something like this. Okay. This is something like this, and what I am going to do here is that for now okay, okay. So, what basically I am telling you here is that in so far this long, okay, for this distance of x, we have a free stream value of the density, and then we have a disturbance which looks something like this, right. So, we have that, and this disturbance is within say here. So, and again we have an ambient. So, what we will try to look at is how this looks like, okay, how this looks like as we go further down x and also in a different instance of time. Okay. This is what we are trying to look at when I say the propagation of a disturbance. Okay. So, what we want to look here is that this disturbance, how this looks like if I go further down in the x direction, right. If I keep going here, how will this look like, or if I go further down in the x direction, what will this disturbance do now? There is nothing new, but the disturbance which is caused, what will that disturbance do? And also, if when I look at it at another instant of time, forward from time t1, what will this look like? Okay. That is what we are trying to study here. So, let us do this. Okay. And let us just what we will do is call this here. So, let us say this is x1. I am also going to do something else here. I am going to draw a local axis system. Okay. Let us call it x naught 1. I am going to draw this local axis system at the origin of this disturbance. Okay. And also we will mark different points, okay, different points on this wave. Okay. Let us say this point is A, right. We have another point which is say B, another point which is C, and this is D. Okay. And this is an so this is basically an amplitude of the disturbance. So, okay. So, that this is what we have at time t is equal to T1. So, let us see what happens to this as we move further down x. Okay. So, let us do that. Okay. So, again I am basically going to try and reproduce the same picture here. Okay. So, we have rho infinity. Okay. So, what happens to this thing here? Okay. Okay. So, now what does this look like as I go further down x? Okay. The way, so this we could just sort of draw it this way. Okay. I am going to just reproduce this. So, which is okay. So, what happens here is that what I try to do here is that this is exactly the same as this one. This is exactly the same as this one, except that this is, you can see that now it has moved. So, therefore, this is you can say the wave fixed axis system. Right? It is exactly the same and it moves from here to here. So, again, so these are the, say this is A, so this is B, this is D, and again this is okay. And now this is x2. Okay. So, what we can see here is that now again, so as I move along x, right. So, I see this happening. Okay. So, I just reproduce exactly the same thing, except that it is slightly further down away from this point, from where it originally originally happened in the flow. Now, is this the correct picture? Now, just think of this. So, essentially with respect to this, if you consider that B, C and D, right, and A, these are say particles within the wave, right. If I consider these as particles within the wave, then you can see that these are the respective positions of B, C and D with respect to the axis system. Right. Now, that does not change as I did it over here as I move it along x. But now, let us just say that this is a picture we are looking at time is equal to T2, right, which is basically, let us just say so basically we are advancing in time, right. So, in that case, in this particular case, if I consider this as unsteady, that this picture also changes. So, in this particular case, as of now, this it is a function of x, right. Now, let us also add to this that this is unsteady, right, that this picture also changes with respect to time. So, when I go from this time to this time, this picture also changes, right. So, if that happens, then how will this picture look like, right. So, let us do this. You can probably guess. Okay. Now, the thing is that, as I just said, that when moving from here to here, okay, so these particles B, C and D, they are exactly in the same respective position with respect to this coordinate system as we move from here to here. But if we consider them as unsteady, if I consider the wave as unsteady, then that will not be so, which would mean then that okay, let's say I will say draw it with this a different color. Okay, so in that case my wave will become something like this. Say something like that. Okay, so this wave, so then in that case this is my say B or say B dash, right? Then this is my C dash and this is my D dash. Okay, so again right. So all I have here, right. So you see the difference. You see the difference between the blue and the orange here, right. So this essentially means that as I, so now for this blue curve, it is no more, just x, right. It is no more just x, right. It is also unsteady. So which means that as I go from t is equal to t1 to t is equal to t2, as I advance in time, my wave, okay, moves along x as well as changes over time. Okay. Now let us see, now the next step, of course, okay, now before we do that of course, is that now this, so say this, if I consider this, okay. Now every time we say this, right, when every time this is not 0 or it is non-infinitesimal, then what we have is a finite wave, right. So okay, so this is it. So therefore all the properties what I have drawn here or try to explain here is basically density. Now you could basically have the same stuff for pressure, temperature, velocity, okay, meaning that I could, and so on and so forth. Okay. Now, so therefore now I can just say that now if I look at two particles, now one particle is say this this particle at C, this particle C dash, or the particle C actually goes from that point C to C dash here. So and let us take another particle somewhere over here and let's call that as particle as P. So we have another particle which is we call that as P. Okay. Now the density of P is rho infinity, of course. Density of P is of course rho infinity. Now if I were to look at this, now this particle say is of course you can see that on the wave it has a certain velocity, right, and that is added to the ambient velocity. So let us just say that the local velocity, locally this velocity is, we can call that as a W. All right, and so when I have mass motion, right, so that local velocity is added to the ambient velocity. Okay, so that becomes the total velocity of the particle over here. Okay, so now also before I finally move on to the governing equations, if you can just remember or try to just recollect that how exactly do waves travel? They travel due to molecular collisions. I hope you can remember that. Okay, so so the point is, okay, let us go back to the table here. So for example, say if I consider, say I am considering these as fluid particles. Okay, I am considering these as fluid particles. Okay, so at some instant of time, this is how the particles are. Look, there is a fluid flow happening, of course. So at some instant of time, say t1, these are certain fluid particles. Okay, and what I do is that I give it a disturbance. I apply a certain disturbance to it. So, now I will apply the disturbance to this particle, to this white particle here. What do you think will happen? Say I apply a disturbance. You saw what happened? I applied a disturbance only to the white particle, but then that particle went and hit this one, that went and hit this one. It did nothing to here, to these, it did nothing to these 3 particles. Let us do that again. Okay, so, what I will do is give it to here. So, in this time it hit the particle, propagated the disturbance from this to this to this. So, when I hit this particle, this hits the next one and the next one and so on and so forth. So, let us just say I will give this particle a slightly larger disturbance. Okay, so, now it goes and hits this one, or say for that matter let us do it even more. So, if I do that, so now you see. So, that is what you see here is that when I give a disturbance here, so it hits the next particle and then it hits the next and so on and so forth. So, this is, so basically disturbance will travel due to molecular collisions, right. Okay. So, now having done that, I think now it is time to go and develop a mathematical theory for all of this, and we will start again from the governing equations, right. Okay. So, let us do that. Okay. So, let us write out the governing equations as we know them, right. So, the governing equations are okay. So, the governing equations okay. Okay. So, this is as you know it. So, this is continuity, this is momentum, and this is conservation laws, right. So, these are your governing equations. Okay. Now, so what I am going to so what we are going to try and do is see how we are going to apply these equations to wave travel, in the sense that we are giving density and pressure and velocity. How do I incorporate the fact that I have a certain velocity, say a density here, and then in this part I have a total density which is equal to the ambient plus the delta rho. So, that is how I take into account the fact that I have a disturbance now. So, let us go and see whether we should be able to do that here. Okay. So, let us see like we just said. So, let the free stream values. Okay. So, we have so free stream values. Okay. Let us denote by subscripts. And so on and so forth. So, let us denote them by subscripts infinity, and local values would be right, local values would be this, and so if I had to do that, so therefore what I would write, so let me write this here. Okay. In that particular case, so therefore my local, say, density would be equal to the ambient plus the disturbance, right. This would be it, and let us call that equation 1, right. And for the velocity, let us say that the initial flow field is undisturbed. If that is so, then right. So, these are the two expressions that we can pretty much write that. Okay. So, now let us do something, let us go ahead and take the continuity equation here given in this one and write it in x direction, right. Let us write it in x direction. So, if I do that, what I get is right, we can write this. So, then again what we will do is we will expand this. So, if I do that, right. So, then I can write it like this. Okay. So, now what we will do here now is that we will use these two expressions which we got in 1 and 2 into this, meaning that this density I can replace by what is given in this relationship here in 1 as the rho infinity as the ambient density plus the disturbance or perturbation, right. And the velocity of course is the ambient is say undisturbed. So, then we have u is equal to delta u, right. If I do that, then what do I get, right. If I do that, so let us in that case what we will get is that say okay, let us write it here. So, what I will get okay. Rho right. This. Okay. Now, if I do this, okay, then you know we will expand this, and finally what we get here is this. Okay. 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 So, what you can see here that del T of rho infinity is a constant, right, rho infinity constant. So, then that does not come in here. So, when I or basically what we are saying is that the ambient obviously remains constant over time, that does not change. So, therefore, this does not come into this equation, and also what else? Yeah, so again here this is also change of the ambient density with respect to the x coordinate, that also does not happen. So, we basically get this equation. So, let us say, so what we get here is this equation, right, and let us say, let us call this as, so this is something that we get from the continuity equation, right. So, again let us come back here, and yeah, so let us look at the momentum equation, and write this. Okay. Now, let us write this in the x direction, right. If I do that, what do I get? Let us again go ahead and say write it over here. Okay, so if I write this, so continuity, so momentum equation in the x direction, if I write it in the x direction, what I get is okay, so we get that, right. And from the third equation, of course, we okay, so we sort of get that, and from the third equation again, now what we get is ds dt is equal to 0. So, which is saying that there is no entropy change over time. What does that mean? That it means that we are considering this as isentropic, right. So, now when I say that, so from this third equation here, we are saying it is isentropic, which means that one thermodynamic variable can be represented as a function of two other. That comes with the definition, which means that okay, let us just do this here. Okay, so let us do this here. So, what I am saying is that we have isentropic, right. If it is isentropic, then I can say, right, pressure, right, as a function of, say, density and entropy, right. I can write it like that. So, in this particular case, in this case, let me write dP, where plus this is just I am differentiating this, right. So, in this particular case, now if it is isentropic, therefore, this should go to 0, right. So, if this goes to 0, what we are left out with is this, that dP is equal to del P del rho at constant entropy into d rho. Okay. So, if this is a thing, so let us write the change of the pressure, change of this pressure in the x direction. That is to say that, right. So, del P del x I can write as so del P del rho at constant entropy into del rho del x. So, this is something that I get from here. So, I find out the change in pressure in the x direction, right. Now, at this point, let us just say that this term here, so, okay, this term here, let's call that as q square. It's just a term, we will come back and find out if that means anything. Let us just call that as q square. Okay. Now, if I do that, okay, if I do this, so therefore, del P del x, okay, so del P del x can be basically said it's equal to q square into del rho del x. In that case, this equation which we wrote out is the momentum conservation equation in the x direction. Then in this one, I can write as, so I can basically write del P del x, replace it by what we just found out, by q square del rho del x, right. I can write this as q square del rho del x, right. So, if this is it, okay. So, now again what we have here is density and velocity. Now, let us go ahead and again incorporate 1 and 2 into this equation. Okay. So, well, let us do that. Okay. Let us do that, and let us see. So, it's a slightly elongated equation, I will write it anyways. Okay. If I do that, what I get is Okay. Okay, and this is equal to this, right. So, this is something that we get. So, what we can see here is that we have now basically this term q square, right. So, I have something in q square. Now, let us see now this is basically now an equation that we will obviously look to solve. So, let us see if we can write this term q square in any other way. Okay. So, let us see if I can do that. So, what I will do is that let us go back and see. So, we basically we defined q square as a derivative of pressure with respect to the density, right, at constant entropy. So, we can also say that basically we are looking at the change in pressure corresponding to a change in density, right. So, del P del rho. So, in that case let us say that if we start, so this q square is basically representing that. So, then let us say that we are starting from ambient conditions, right, pressure and density ambient conditions, and to that we are adding changes. Okay. So, therefore, how do I find out that particular change? So, let us use a Taylor series, mathematically Taylor series. So, if I do that, okay. So, okay. Now, what we have seen here, yeah. So, basically q here, q is essentially okay. Let us see, rho density is rho. Yeah. So, this now this term here, okay, q square, this is a function of. So, basically this is a function of the density and entropy, right. It is a function of density and entropy, but then entropy here is constant. So, we can just say that this is basically tracking the change of the pressure, right. Then change of pressure, in that case what we will just so let us say we will write this as now q say, okay. Okay. So, if I do this, okay. So, now I am going to write this in the Taylor expansion of this q square, right. So, if I do that, so let us say q infinity square, right. Right. Okay. So, this is the expansion. So, then I can again write this as, or okay, let us write this as delta rho. Okay. So, what this becomes, and so on and so forth. So, then this becomes right. So, q square is something that I can write like this. So, therefore, now if I were to combine, if I were to combine these equations, okay. So, if I were to combine this 2 and 3, right, for the so essentially we combined that and we got this this in the x direction, right. And what we have done here is found out an expression for this q square in terms of the perturbation, right. Now, if I write this out, what does this look like? Okay. So, I am going to write that down right underneath the equation 3 here. So, if I write this, what I get is, so you can see that basically I am going to expand this and incorporate q square, which I just derived. If I do that, what I get is okay. So, that is equal to right this thing. So, now this equation okay. So, to kind of summarize, what we have done here is we took the governing equations. We took the governing equations, incorporated the existence of a disturbance. How? By saying that it comes as the disturbance is basically causing a perturbation to the variables, right, thermodynamic variables. So, which we did like this. Okay. Then we wrote out these equations in the say x direction. So, we wrote out these equations in the x direction, right, and we were able to come up with the equations 3 and 4, right. So, this is the governing equations, right. The equation 3 came from the continuity equation and equation 4 came from the momentum equation and the energy equation. So, when we got these two equations, so this is basically the governing equations, taking into account that we have a disturbance and that is being shown by the perturbations in the thermodynamic properties. Okay. So, you can see that our task here is to solve for this. Once we solve for this, then we should be able to get a figure get a hang of the way we were trying to study the disturbance. Okay. So, of course, you can see that this is numerically pretty exhaustive, right. So, the first thing we will do, right, is see if we can get something very simple from here. And the first thing that we can see from here, if I take something simpler, is that we will consider the wave or the disturbance to be very weak. Like I just showed you as the part when I was hitting the particles, that if I hit it slowly, the disturbance travels slowly, right. So, let us just say it is a very weak wave. What does that mean in terms of the perturbations here? Okay. So, if I do that, let us just say, let us do that here. Okay. Okay. Now, so in this particular case, so let us just say that right. So, this is essentially, now we are saying the disturbance is very small. So, the perturbations are very small compared to the ambient. Okay. So, it is a very weak disturbance, very weak wave. Okay. So, so in that case, what does it signify mathematically? What happens to these mathematical equations that we just derived from here? Right. So, let us look at equation 3. Now, what we get from equation 3 is something like this. Okay. Right. If I make this assumption that delta rho and delta u are very small compared to the ambient, you can see here that I am multiplying basically a very small amount with a derivative of a very small amount. So, these two essentially become very small. In a quantity it becomes very small. So, I can basically I will take it out of my equation. So, I can therefore write equation 3. So, equation 3 therefore reduces to, therefore, this is from equation 3. So, this is 3 actually, this reduces to, and let us call this as 5. So, similarly, we will do the same thing with equation 4, right. We will do the same thing with equation 4, right. And what we get from here, okay. So, what we get from here is, right. Okay. Now, I think we are in a very good space to look at the two equations. Now, what we can now, these equations, equation 3 and equation 4, these are exact equations. This is exactly the governing equation. We put in our requirements. So, these are two exact equations, and hopefully you can see that these are nonlinear as well, right. So, these two equations 3 and 4, right. So, 3 and 4 are essentially nonlinear and exact, right. Now, come here, and what we do is we assume that the disturbances are very small. So, let us say we make a small perturbation assumption, right, which means it is a very weak wave. Okay. What is the weakest form of traverse? The sound wave, right. So, therefore, let us just say a sound wave is something that we are trying to look at here. So, in that case, the equations, therefore, the exact nonlinear equations reduce to equations 5 and 6. And you can see the mathematical property here that these are linear, right. So, these are linear, but also approximate. Okay. So, now these two equations on the other hand, 5 and 6 on the other hand are approximate they are also called as acoustic waves, right. I hope that is kind of intuitive, because as we are looking at, we are using these equations to be for very small disturbance. So, for very weak waves, right, which could be for sound waves. So, in that particular case, the changes would be given like something like this. So, we come about this. So, therefore, the way we get equations 5 and 6 is using a small perturbation theory along with a linearized theory. Okay. So, now okay. So, now what we will do here is a is there something else now? I need 5 more minutes. Okay. So, he said 350, yeah, just 5 more minutes I need. Okay, so now what we will do here is do some manipulations, okay, with these equations that we've got, right, with these equations 5 and 6, etc., and see if we can get some more information, because now the point is that once we have, so now this is basically our governing equations. Now what we have to do is find a way to solve these. That's our next step. So what we will do here is in order to solve this, so okay, now let us, in order to do that, okay, so what we'll do is, first is, let's do this. So let's do a del del t of equation 5, right? What we get here is right, and similarly let us do del del x of equation 6, right. If I do that, what I get is right. Now once I do that, then I subtract equation a minus b, and what I get from there is this. Right. So this, let's call this as equation. Let's call this as equation 7. Okay. Now again, so again similarly, what we will do is del del x. So okay, I'm not going to write that again. You could do it yourself. So we can write del del x, right? Del del x of equation 5, right? And let's just do this. So what we'll do is del del t of equation 6 minus del del x of equation 5, right. This is what I do. This is what I do, and what I get is this. Seven and 8, right. So what you can see, so therefore what you see over here is basically I have two equations. I have two equations in delta rho and the other in delta u. So once I'm able to solve these, I should be able to figure out what my perturbations are, right. So now the beauty of these two, the way we have these equations, equations 7 and 8, that we have ready-made solution, because this is, I hope by this time this equation should be familiar to you, right. So this is a standard equation, right, and therefore I can write out the, for example, yeah, so this I can write as right. And similarly, where f, g are all arbitrary functions. They are arbitrary functions, right. So what we have done if I were to look at this. So now what we will do is solve for see what this solution holds for us, how this will look. So this we will do in the next lecture. Now the only the place where I will stop today is that what we did is that we looked at a picture like this. We looked at a picture like this and we said that when this is not 0 or this is not like really small, then what we have is a finite wave. We found out the equations, how the governing equations would look for a picture like this when I take into account these perturbations of for the disturbance to propagate, and what we came out with are the equations 3 and 4. Now to solve this and to decrease the complexity of to solve this, what we did was we said, hey, you know, this is complicated, this is too long. So we went and assumed we made a small perturbation assumption, and what we came up are these two equations, which are approximate but linear, and we played around with those and we found out further an expression for delta rho and delta u, which is what we set out to do right at the beginning. Now the question is that the way we got delta rho and delta u, now this is after we made we used a small perturbation theory and a linearized theory. Now so therefore this, now what we need to look at is that how this will change the picture, or will it? Now is this still valid for something like this, because we have now considered that this perturbation is very small. That is something we will look at in the next class. Thanks.